Okay, this week we're going to interpret graphs using patterns estimation, interpolation, and extrapolation, and we're going to solve linear equations using graphs. For this week, you can use this video as a resource, and for extra practice, your workbooks 4.4 and 4.5. Alright, so to begin, let's go over the two new words that you see in the goals. Okay, interpolation and extrapolation. So interpolation, when you're estimating a value between two given values. Okay, so when you have a graph and you are estimating a value between those values, you're interpolating. Okay, you're extrapolating when you are estimating beyond the given set of values. So if you have a graph and you have to estimate what's outside of the graph, that's extrapolation. Okay, it will become more familiar as we try the questions and use these two methods. All right, last week you learned how to graph given equations or table of values. If you think you need more review of graphing equations, there is some extra practice on graphing linear equations on D2L, and there's an extra video that goes over graphing as well. So please take a look at that resource if you're struggling to graph data. All right, so let's move on to our first question. It says, this table of values represents the distance that Zoe cycles in relation to time. So it shows us that for every hour she cycles, the distance that she goes. Okay, first part, it's asking us to plot this linear relationship on a graph. So this is something that we did last week. This is very simple to do when you're given a table of values, right? So we're going to graph it on the graph that I have below here. And we have to think about, okay, what goes on our x-axis and what goes on our y-axis. Because distance depends on how much she rides, x-axis is going to be our time. So this is our time in hours, it says. And then our y is going to show the distance. And this is our distance in kilometers. All right, and then for the units, okay, we need to go from 0 to 6 for x. So we start at 0, and we can go 1, 2, 3, 4, 5, 6 on our x-axis. And for distance, I need to go all the way to 80. So I might go 10, 20, 30, 40, 50, 60, 70, 80. Let's see if I can do this by counting by 10, 20, 30, 40, 50, 60, 70, and 80. Okay, perfect, it worked. Okay, now I have my x and my y-axis, and I just have to plot the points. So the first point that I have is when x is 1, y is 12.5. So when x is 1, I go to where 12.5 is, approximately right here. When x is 2, y is 25. So when time is 2, distance is 25. And when 3, it is at 37.5. And when at 4, at 50. Okay, I don't have to do all of these because when you end up connecting the line, you get a straight line because it's a linear relation, right? So let's go to our last one. I go to 6 and all the way to 75, and I just have to connect the dots. Okay, so I know that this continues on, except it'll only go to 0 because you can't bike for minus 1 hour, right? So this starts at 0, 0, and it will go on forever because she can bike for however long she wants, right? All right, now that we have a graph, we have to determine the approximate distance that Zoe has cycled after 2.5 hours. Okay, so let's actually look at how we can get this data. Okay, so you have to look at the time at 2.5. How much does she actually bike? It looks like it's around 30 kilometers. So that's our answer for B from the graph. Zoe cycles 30 kilometers after 2.5 hours. This method, we just use interpolation because we use data within the linear graph that we drew. Our data that we got is within this graph. Okay, so this was interpolation. All right, and then let's look at what would it From the graph, approximate how long it takes her to cycle 44 kilometers. Okay, now our distance is represented on our y-axis. So for that question, we actually have to start at the y-axis and go where 44 is approximately, and then see how long it takes her to get to that point. So the x value of that point will tell us, and it's about 3.5 hours. So we say 3.5 hours. Same thing here. This was also interpolation because it's within the range of our graph. Okay. All right. Looking at D though, it says estimate how long it will take her to cycle 100 kilometers. We don't have that on our graph. Okay. But if we were to extend it out, we can kind of estimate, although this only goes to 90 and 100 would go out of the graph. We would just continue, and approximately at what time does she reach 100 kilometers? Okay, so we had to extend our graph out. We had to extend our graph, and that's the process of extrapolation, because you went out of the graph, out of the range of data that was given to us to estimate how long it will take her to cycle 100 kilometers. It looks like it's just below 10 hours, so we can go approximately 9.5 hours. Okay, and this is extrapolation. Okay, one more time. So B and C, it was asking us to approximate distance at the distance that she went after 2.5 hours. So we start at 2.5 and got the distance. And here, how long does it take to cycle 44? 44 is approximately here, and we look at the time it will take her to get to that point. These were within the range of values that were given to us, so it's interpolation. Okay, while the last one, it asks us for a point that's outside of the range of our graph, but we can still extend it because it's a linear relation. That's extrapolation. Okay, that's it. So we are using our graph to answer these questions. So that's why we call this unit, we're interpreting our graphs. Right? Let's look at the next part. Okay, other than interpreting graphs, we also want to be able to solve linear equations using graphs. Okay, so when we have a linear equation, y is equal to negative 3x plus 10. Okay, what is the value of y when x is 1? So it's asking us for what is y when x is equal to 1. Okay, a lot of you might be thinking, okay, we can just substitute in the value of x into our equation and solve algebraically, okay? But we want to solve this using graphs, and we can do that by using the graph that's shown to you. We go to, so this is the graph of this equation right here. We go to when x is equal to 1. It's not here because look at our scale, it goes to 10 over here, right? It's divided into 1, 2, 3, 4 chunks. So this point actually tells you approximately 2.1. Okay, so 1 would actually be somewhere over here, and it looks like it is around this point right here. And same thing here, it goes 2, 4, no, it actually goes 3, 6, 2.25, 2.55. It's broken down into 4 parts, so this is actually 2.5, 5, and 7.5. Okay, and 1 is somewhere just below that number. Okay, so we can say it's approximately around 7 to 7.5. Okay, sometimes, okay, so depending on the graph that you have in front of you, sometimes you need to estimate the values, or sometimes it might be easy to see which value it falls on right away. Okay, so for us to figure out what the value of y is when x is 1, we go to when x is equal to 1 and read the value of y over here. Okay, so now this is the same thing. We're just going to read the graph when x is equal to negative 1. Again, it's the same scale over here, so negative 1 is around here somewhere, and it goes just above 10. Okay, it just goes just above 10, so it is around, we can say, it's around, so y is approximately, so we use strict squiggly lines, around 10. Okay, To confirm your answers, you can use this, do this algebraically. You go y is equal to -3, and in place of x, I'm going to place -1, and that gives us 3 times 1 is 3 plus 10, y is equal to 13. Okay, so if you look at our graph, let's see if that is proven by our graph. So when we go to x is -1-ish, it was just above 10. Okay, so it has to be greater than 10. Okay, so this works with our graph. Okay, same thing, we can check this one algebraically by just plugging in the value of x. Okay, and y is equal to -3 plus 10, which is equal to 7, and our approximation is very close to that. Okay, so you can solve equations using graphs, okay, by reading the graphs, and then you can confirm it by solving it algebraically, which you're familiar with doing. All right, you will see word problems in this unit. Okay, let's see, it says at bulk barn, trail mix costs $2.40 per 250 grams. Using a graph, approximate how much 2,000 grams of trail mix would cost. Using a graph, approximate how much trail mix you would get for $13. Okay, so this is what the question wants us to do. We need to have a graph first. Okay, so let's think about what our graph will look like. It only gave us this. Okay, that's just 1 point. It costs us $2.40 for 250 grams. But we can do the math, and we know that for 500 grams, which is double that, it will cost us $4.80. Okay, let's do one more. What if I add another 250 grams? Okay, that would give us $7.20 for 750 grams. All right, and so on. So now I have, from one set of data, I have 3 points that I can graph on my graph. Okay, because this information was enough to tell us that it's a linear relation. It just goes up by 240 for every 250 grams. Right? Now, what is our x-axis and y-axis? What depends on what? So the cost is going to depend on the amount of trail mix you're going to get. So on our x-axis is going to be the amount, and on our y is going to be the cost. Okay? So on our x-axis, we want to go from 250 all the way to 2,000 for us to be able to approximate it. So we can go maybe 500 over here, and 1,000, 1,500, and then 2,000, 2,500, like this. And this is amount in grams. All right, and then our y is the price, and we want to go all the way to 13, 4, 5, we can go up by 2, 4, 6, 8, 10, 12, 14, and this is the price. Price in dollars. Okay, we have these points to graph now. So for 250 grams, at 250 grams, it's going to cost us just over $2. So it goes somewhere over here. Okay, at at 500 grams, it's going to cost us $4.80. So we go somewhere over here. At 750 grams, it's going to cost us $7.20. So it goes somewhere over here. So this is the graph that we have from the data. Okay. Using the graph, and then we know that this can also actually extend forever and ever, because you can get unlimited, whatever amount of trail mix you want, right? All right, using the graph, approximate how much 2,000 grams of trail mix would cost. You go to 2,000 and the amount from the x-axis, and you go up to where that meets the y-axis, and it looks like that's about 15. So $15. So we say approximately $15 for 2,000 grams. Okay, and then the other one, they want us to approximate how much we can get for $13. Dollars is on our y-axis, so you go to 13 on our y-axis, and you go to the point that is on our graph, and that is approximately just below 1,750 grams. So we go approximately 1,700 grams for $13. Okay. So depending on what the question is asking you, you might be starting at your x-axis or your y-axis. Okay, but again, in the word problems too, you're interpreting the graph that you have to answer the questions. Okay. So for this week, you're going to complete week 9 task 1, take a picture of it and upload it under assignments. There's no quiz this week. Okay, so you just have to worry about doing the task.